Did you know that, at this very moment, while you're here with me, at least 3 stars are exploding somewhere in the universe? In just 1 second. These explosions released more energy than our sun will produce during its entire 10 billion year existence. Hello? Where are you right now? Perhaps relaxing after an intense day, or simply seeking a moment of contemplation before sleep. Regardless of where you are, I'm happy you've chosen to spend this time with me exploring one of the most fascinating phenomena in the cosmos. If this content sparks your curiosity about the universe, consider subscribing to the channel and leaving a like on the video. It really helps me continue bringing these cosmic journeys to you. Now, close your eyes for a moment and imagine with me, somewhere very far from here, at this exact moment, a star is dying. But this isn't a silent or melancholic death. It's an explosive, brilliant death, so intense it can be seen from billions of light years away. Have you ever wondered what happens when a star, those cosmic beacons that illuminate our nights, reaches the end of its journey? What forces these celestial giants, which have shone majestically for millions or billions of years, to explode in one of the most powerful manifestations in the universe? This is the story of supernovas, and I promise that by the end of this narrative, you'll never look at the sky the same way again. Prepare to discover how the violent death of a star can be, paradoxically, the cradle of life. How elements forged in the nuclear heart of cosmic giants are scattered through space, creating conditions for planets to form, atmospheres to develop, and eventually for life itself to flourish. Have you ever thought about this? That perhaps everything you are, every atom in your body, every breath you take, is the legacy of a star that exploded billions of years ago? Supernovas are more than distant astronomical events. They are the architects of the cosmos, the creative forces that shaped the universe we live in. They are phenomena so powerful that a single explosion can release more energy in a few seconds than the sun will produce during its entire 10 billion year existence. Imagine the magnitude of this, all the heat that has warmed Earth since it formed. All the light that has sustained life for countless ages, all that solar energy concentrated in an instant of indescribable cosmic violence. But within this violence lies a profound poetry. Because it's through death that stars give us life. It's through destruction that they create the seeds of new worlds. And it's through their extinction that they light the torches that will illuminate the future of the universe. Tonight I invite you to close your eyes and travel with me through time and space. We'll witness the birth and death of cosmic giants. We'll understand how these explosions work that make entire galaxies tremble. And we'll discover, in the end, that you're much more connected to the stars than you ever imagined. To truly understand what supernovas are, we first need to dive into the intimate life of stars. Imagine, if you can, a cosmic factory that has been operating for billions of years. An energy plant so efficient that it transforms the simplest elements in the universe into the fundamental building blocks of existence. This is what a star represents, a natural nuclear reactor of unimaginable proportions. In the heart of every star, there's an epic battle constantly raging. On one side, we have gravity, that relentless force pulling everything toward the center, trying to compress the star until it collapses upon itself. On the other side, we have nuclear radiation pressure, the energy released by the fusion of hydrogen into helium, pushing outward with tremendous force. During most of a star's life, these two forces remain in delicate balance, like two cosmic dancers spinning in perfect harmony. But have you ever wondered what happens when this dance comes to an end? When the nuclear fuel begins to run out and the balance is broken. That's where our story truly begins, at the frontier between stellar life and death. Think for a moment about the sun, our nearest star. It burns approximately 600 million tons of hydrogen every second, converting them into helium and releasing an amount of energy equivalent to 100 billion hydrogen bombs exploding simultaneously. And this happens every second without stopping for more than 4.5 billion years. Impressive, isn't it? But even this colossal energy production pales before what we'll witness when we talk about supernovas. The sun is a medium-mass star, destined for a relatively peaceful retirement. In a few billion years, it will expand to become a red giant, possibly engulfing Mercury and Venus, before ejecting its outer layers and becoming a white dwarf, a dense remnant the size of Earth, but with the mass of an entire star. It's a dramatic end, but not violent. But there are stars much more massive than the Sun, stars with 10, 20, 50, or even 100 times the solar mass. These live completely different lives, more intense, brighter, and infinitely shorter lives. Where the Sun burns hydrogen conservatively, like an economical engine, these massive stars consume their nuclear fuel as if there were no tomorrow. And indeed, for them, there isn't. A star with 20 solar masses might live only 10 million years, a tiny fraction of the universe's age. During this time, it shines with the intensity of tens of thousands of suns. It's like a candle burning from both ends, producing dazzling light but doomed to extinguish quickly. And when these giant stars die, they don't go gently. They explode with a fury that illuminates entire galaxies, creating spectacles of light and energy that can be seen billions of light years away. This is the phenomenon we call a supernova, the final cry of a dying star, a cosmic lament that echoes throughout the universe. Before we dive into the explosive death of stars, I need to tell you about one of the most poetic discoveries of modern science. Did you know that you are literally made of stardust? This isn't a romantic metaphor, it's an extraordinary, scientific fact that connects your existence to the life and death of stars. In the beginning of time, shortly after the Big Bang, the universe was a simple and monotonous place. Only 3 elements existed: hydrogen, helium, and a pinch of lithium, nothing else. No carbon, no oxygen, no iron, none of the elements that compose your body at this moment. All these elements were forged inside stars through a process scientists call stellar nucleosynthesis, a technical term to describe the most fascinating cosmic alchemy that exists. Imagine the interior of a star as a cosmic kitchen with multiple ovens operating simultaneously. In the innermost oven, hydrogen is transformed into helium through nuclear fusion. This is the reaction that fuels the Sun and most stars during the majority of their lives. 4 hydrogen nuclei combine to form 1 helium nucleus, releasing energy in the form of light and heat. When the hydrogen in the core is exhausted, something fascinating happens. The star doesn't simply die. It reinvents itself. The helium core contracts and heats up until it reaches temperatures sufficient to ignite helium fusion. Now we have a new cosmic oven. 3 helium nuclei combine to form carbon, while adding another helium nucleus to carbon creates oxygen. Can you visualize this alchemical progression? It's as if the star were a cosmic chef, constantly creating new dishes from the ingredients it has available. And as the star ages, it develops a layered structure like a celestial onion. In the core, heavy elements like carbon and oxygen. In the next layer, helium. In the outer layers, hydrogen. For sufficiently massive stars, this process continues. Carbon fuses to form neon, magnesium, and sodium. Oxygen creates silicon, phosphorus, and sulfur. Each new fusion reaction requires higher temperatures and happens more quickly than the previous one. If hydrogen fusion can last billions of years, carbon fusion lasts only thousands of years. Oxygen fusion, just a few years. Silicon fusion, days or weeks. And finally, in the heart of the star, the element that will be crucial to our story forms: iron. Have you ever thought about this? The iron running through your veins, strengthening your muscles, was created in the burning heart of a massive star billions of years ago. Every iron atom in your body passed through the nuclear furnace of a giant star, experiencing temperatures of hundreds of millions of degrees. But here's the fascinating twist. Iron marks the end of the line for nuclear fusion. Unlike all other elements, iron fusion doesn't release energy, it consumes energy. It's as if the star, after feeding its nuclear furnaces for millions of years, suddenly found itself with fuel that, instead of burning, extinguishes the fire. This is the crucial moment in the life of a massive star. Throughout its entire existence, it maintained a delicate balance between gravity trying to compress it and nuclear radiation pressure pushing outward. But when iron forms in the core, this balance is dramatically broken. Ion fusion absorbs energy instead of producing it, and suddenly the pressure that sustained the star disappears. It's like all the pillars supporting a gigantic building were removed simultaneously. Gravity, which waited patiently for millions of years, finally has its opportunity. And when it acts, it's with a violence that redefines our understanding of the word explosion. Let's now approach the critical moment in the life of a massive star. Imagine a star with at least 8 times the mass of our Sun, a true cosmic giant that has dominated its corner of the universe for millions of years. Throughout its entire existence, it maintained the perfect balance between gravitational collapse and nuclear radiation pressure. But now, something dramatic is about to happen. In the core of this giant star, iron accumulates like nuclear ash in a cosmic fireplace. Unlike previous elements, iron is an energetic dead end. In the periodic table, iron occupies a special position. It's the most stable element. This means that fusing lighter elements to form iron releases energy, but fusing iron to form heavier elements requires energy. For millions of years, the star functioned as a perfect energy conversion machine. Every fusion reaction in its core released energy that created the pressure necessary to resist gravitational collapse. But now, with an iron core, this machine hasn't just stopped working, it has started working in reverse, consuming energy instead of producing it. When the iron mass in the core reaches approximately 1.4 times the mass of the Sun, a limit known as the Chandrasekhar mass, named after Indian astrophysicist Subrahmanyan Chandrasekhar who discovered it, something catastrophic happens. This limit represents the point where not even the degenerate pressure of electrons can resist gravitational compression any longer. Suddenly, without warning, the radiation pressure that sustained the star for so long disappears. It's like all the pillars of a gigantic building were removed simultaneously. Gravity, that patient force that waited millions of years for this moment, finally wins. And when it wins, it's with a violence that defies imagination. The star's core collapses upon itself in a fraction of a second. In less than 1 second, the time it takes you to blink your eyes, a core the size of Earth contracts to form a sphere only 20 kilometers in diameter. Imagine compressing all the mass of our planet into a sphere smaller than a city. The density becomes so extreme that a teaspoon of this material would weigh as much as Mount Everest. During this collapse, the temperature rises to over 100 billion degrees, 6,000 times hotter than the Sun's core. The pressure reaches values so extreme that protons and electrons are literally crushed together, forming neutrons and releasing a torrent of neutrinos, ghostly particles that rarely interact with matter. Can you visualize this cosmic violence? It's as if the universe were concentrating all its fury into a point smaller than a city. The physics we know on Earth simply no longer applies. Conditions are so extreme that the very structure of matter is redefined. And then, in a moment that defines the fate of entire solar systems, something extraordinary happens. The outer layers of the star, still falling toward the core at free-fall velocity, collide with the ultra-compressed core and violently rebound outward. It's like a bowling ball colliding with a diamond wall. All the impact energy is redirected back upward. This cosmic collision generates a shock wave so powerful that it redefines our understanding of the word explosion. The energy released in a few seconds is equivalent to the energy the Sun will produce during its entire 10 billion year life. It's so much energy concentrated in so little time that it makes the star shine more intensely than an entire galaxy. The stellar core collapse generates a shock wave so powerful that it redefines our understanding of the word explosion. When the free-falling matter hits the ultra-compressed core, it rebounds like a ball bouncing off concrete, but with energy billions of times greater than any explosion ever witnessed on Earth. This shock wave travels through the star at speeds of up to 30,000 kilometers per second, approximately 10% of the speed of light. Imagine a wall of energy and heat moving faster than anything we can conceive on Earth, vaporizing everything in its path. Entire layers of the star, each containing precious elements forged over millions of years, are swept into space in a matter of hours. But here's the most impressive aspect. In just a few seconds, this explosion releases more energy than our Sun will produce during its entire 10 billion year life. To put this in perspective, imagine that all the energy the Sun has produced since it formed, all the light that warmed Earth, all the energy that sustained life for ages, were concentrated into a few seconds. That's the magnitude of a supernova. It's so much energy that, for a few weeks, a single supernova can shine more intensely than an entire galaxy containing hundreds of billions of stars. Imagine this, an object the size of a star producing more light than 100 billion stars combined? It's like a single candle suddenly becoming brighter than all the spotlights in the world together. Have you ever wondered what it would be like to witness this spectacle up close? Obviously, close in cosmic terms means a few dozen light years away. Anything closer would be fatal to any form of life. But imagine if we could observe safely, we would see an ordinary star suddenly explode in a flash of light, so intense it would outshine all other stars in the night sky. During the first days after the explosion, the supernova would emit as much light as 5 billion suns. It would be visible during the day, casting shadows at noon like a second moon. At night, it would be possible to read a book just by its light, and it would be the brightest object in the sky, surpassing even Venus or the full moon. This extraordinary brightness isn't just a cosmic light show. It's the universe performing one of the most important transformations in physics, converting matter into pure energy according to Einstein's famous equation. E equals mc, the supernova explosion releases so much energy that part of the star's mass is literally converted into pure light. But the shock wave does more than just create light. As it propagates through the star's layers, the extreme conditions of temperature and pressure allow the creation of elements that could never be forged during the star's normal life. During these violent moments, atomic nuclei are bombarded with neutrons so intensely that elements heavier than iron are created in abundance. Gold, silver, platinum, uranium, all these precious and rare elements are forged during the first seconds of a supernova explosion. The gold ring you might wear, the gold in electronic circuit boards, every gold atom in the universe was created during these terrifying moments of cosmic violence. And then, after vaporizing the star's outer layers, the shock wave roars out into interstellar space, carrying with it all these newly created elements. It's as if the star were distributing its chemical inheritance to the cosmos, spreading the ingredients of complexity across light years of distance. This expansion continues for millennia. The shock wave, now called a supernova remnant, continues propagating through interstellar space at thousands of kilometers per second, pushing and heating the surrounding gas, creating filamentary and colorful structures that we can observe through modern telescopes. Not all supernovas are born the same way, just as not all life stories end in the same manner. Astronomers have identified different types of supernovas, each with its own cosmic personality and explosive peculiarities. Understanding these differences is like learning to distinguish between different types of storms. Each has its unique characteristics, but all share the power to transform the landscape around them. The type we just described, the core collapse of a massive star, is known as a Type II supernova. These are the most dramatic in terms of physical process, born from the death of stars that lived fast and died young. Stars with more than 8 solar masses burn their nuclear fuel so intensely that they exhaust their reserves in just a few million years, a tiny fraction of the universe's age. These Type II supernovas can be identified by the presence of hydrogen in their light spectra. During the explosion, the hydrogen-rich outer layers are ejected, and the light from the explosion, passing through this material, carries the characteristic spectral signatures of hydrogen. It's as if the star were leaving its fingerprint in the light it emits during its final moments. But there's another type of supernova, equally fascinating and perhaps even more intriguing, Type Ia supernovas. These are born not from the solitary death of a giant star, but from a cosmic drama involving two stars in a destructive relationship, a true love affair that ends in cosmic violence. Imagine a small and extremely dense star, a white dwarf, which is what remains when a star like the Sun reaches the end of its life. A white dwarf is a fascinating object in itself. It contains approximately the Sun's mass compressed into a volume the size of Earth. It's so dense that a teaspoon of its material would weigh as much as an elephant. Now imagine that this white dwarf has a nearby companion, a normal star orbiting around it in an intimate gravitational dance. The white dwarf, with its intense gravity, begins to steal material from its companion, like a cosmic vampire slowly feeding on its victim. This process can last millions or billions of years, with the white dwarf gradually gaining mass at the expense of its companion. As the white dwarf accumulates more mass, something critical approaches. Remember the Chandrasekhar limit we mentioned before, approximately 1.4 solar masses. When the white dwarf reaches this critical mass, it can no longer support itself. But here, instead of a gradual collapse followed by a rebound, we have something even more dramatic, an instantaneous explosive ignition. The entire white dwarf, an object the size of Earth with the mass of the Sun, explodes like a gigantic thermonuclear bomb. In a matter of seconds, the entire star is converted into energy and heavy elements. It's like someone throwing a match into a cosmic barrel of gunpowder, but with violence that releases energy equivalent to billions of hydrogen bombs exploding simultaneously. Have you ever thought about the irony of this situation? A star that already died once, transforming into a white dwarf, finds a second death even more spectacular. And this second death is so violent it can completely destroy the star, not even leaving a dense remnant behind. It's the total annihilation of an object that contained the mass of an entire star. Type Ia supernovas are particularly important for astronomy because they're extremely consistent. Since they all explode when the white dwarf reaches exactly the same critical mass, they have approximately the same intrinsic brightness. This makes them perfect standard candles for measuring cosmic distances. We know how bright they should be, so we can calculate how far away they are by comparing their apparent brightness with their actual brightness. There's still a third category, rarer and more mysterious, peculiar supernovas. These include events like hypernovas, which are explosions even more energetic that release 10 to 100 times more energy than a typical supernova. We also have superluminous supernovas, which shine hundreds of times more intensely than common supernovas, challenging our understanding of the physical limits of these explosions. Each type of supernova tells a different story about the life and death of stars, about the extreme physical processes that govern the universe, and about the ways matter and energy can be transformed under the most extreme conditions imaginable. Now we come to the poetic heart of our story. Supernovas aren't just destructive events, they are, paradoxically, the greatest creative forces in the universe. When a star explodes, it scatters through space all the elements it manufactured during its life, and the explosion itself creates even heavier elements that could never be forged under normal conditions. During the first seconds of a supernova, temperature and pressure conditions are so extreme that atomic nuclei are literally bombarded against each other with unimaginable violence. Free neutrons created during the core collapse are captured by existing atomic nuclei at an astonishing rate. This process, known as rapid neutron capture, allows the creation of elements much heavier than iron. Think about this for a moment. The gold ring you might wear on your finger was created during a few terrifying seconds in the death of a massive star, probably billions of years before Earth even existed. Every gold atom in the universe went through this traumatic and extraordinary experience. It was forged in the infernal cauldron of temperatures of 100 billion degrees and pressures that crushed the very structure of matter. But it's not just gold. The silver in your jewelry, the platinum in automotive catalysts, the uranium that powers nuclear plants, all these precious and rare elements were born during the most violent moments a star can experience. It's as if the universe chose its most extreme moments to create its rarest jewels. The real magic, however, happens after the supernova's shock wave spreads through interstellar space. It carries with it all these newly created elements, distributing them across dozens or hundreds of light years of distance. It's as if the universe were a gigantic garden and supernovas were cosmic gardeners, spreading seeds of chemical complexity wherever they go. These seeds, atoms of carbon, oxygen, silicon, iron, and dozens of other elements, travel through space at thousands of kilometers per second, mixing with existing interstellar gas. Eventually, they condense into clouds of interstellar gas and dust, creating chemical nurseries where new stars and planets can form. Imagine an interstellar cloud as a primitive cosmic soup. Initially, this soup contained only the simplest ingredients, hydrogen and helium. But as generations of stars lived and died, successive supernova explosions enriched this soup with increasingly complex ingredients: carbon to form organic molecules, oxygen to create water, silicon to form rocks, iron for planetary cores. Over time, gravity does its patient work, gathering this enriched material to form new stars. But now, the second and third generation stars aren't alone. They're accompanied by disks of material containing all the elements necessary to form rocky planets like Earth. Are you beginning to see the connection? Your body contains calcium forged inside a massive star billions of years ago. The oxygen you're breathing right now was created during helium nuclear fusion in a giant star. The iron in your blood, which transports oxygen to every cell in your body, was born in the final moments of a star's life that exploded long before the solar system existed. You are, literally, a child of the stars, a temporary arrangement of atoms that traveled through the cosmos for billions of years before coming together to form you. Every breath you take contains atoms that were once part of distant stars. Every heartbeat is possible because of elements created in nuclear furnaces of unimaginable temperatures. Carl Sagan, the famous astronomer and science communicator, expressed this cosmic connection poetically. We are made of star stuff. But this isn't just a beautiful phrase, it's a literal description of our origin. We are direct products of stellar explosions, temporary manifestations of the universe's tendency to create increasing complexity through cycles of cosmic birth and death. And the story doesn't stop there. The elements scattered by supernovas don't just form planets, they make possible the complex chemistry necessary for life. Carbon forms the complex molecular chains that are the basis of all biology. Oxygen enables respiration. Phosphorus is essential for DNA, sulfur for many proteins. All these crucial biological elements are direct products of supernova explosions. The influence of a supernova on the universe doesn't end with the dispersal of elements. The shock waves that propagate through interstellar space play a fundamental role in forming new stars, creating a cosmic cycle of death and rebirth that is one of nature's most beautiful dances. Imagine the space between stars not as a void, but as a tenuous ocean of gas and dust. This interstellar medium seems empty compared to terrestrial standards. But on cosmic scales, it contains trillions of tons of matter spread across light years of distance. Most of the time, this gas remains diffuse and relatively cool, floating peacefully through the cosmos like mist on a calm morning. Then suddenly, a supernova's shock wave crosses this region like a cosmic tsunami. The pressure and heat from the explosion compress the interstellar gas, creating denser and hotter regions. It's like someone squeezing a wet sponge. The material concentrates in certain areas, reaching critical densities that would normally take millions of years to develop naturally. When these compressed regions reach sufficient mass, something magical happens. Gravity takes over and gas clouds begin to collapse upon themselves. Within these collapsing clouds, temperature and pressure gradually increase until, in the densest center, nuclear fusion ignites and a new star is born. Can you perceive the poetry in this? The violent death of one star triggers the birth of dozens or hundreds of new stars. It's as if the universe developed a mechanism to ensure that light never completely goes out. Each supernova is simultaneously an end and a beginning, a conclusion and a promise of cosmic renewal. But the process is even more intricate and beautiful than that. Shock waves don't just compress gas, they also create complex and organized structures. As the wave propagates, it pushes material into filamentary patterns, creating dense corridors where star formation is more likely. It's as if the explosion were sculpting interstellar space, creating a cosmic architecture that favors the birth of new stars. Some of the most spectacular star-forming regions we know, colorful, nebulae that look like cosmic paintings, are direct or indirect products of ancient supernova explosions. The famous Orion Nebula, visible to the naked eye as a small bright patch in the constellation Orion, is a stellar nursery where hundreds of young stars are being born, possibly triggered by shock waves from supernovas that exploded millions of years ago. When we observe these nebulae through telescopes, we see true cosmic maternity wards. Within the clouds of glowing gas, small dark nodules mark locations where new stars are condensing. Some of these nodules have already developed disks of material around them, the first signs that planetary systems might be forming. It's an extraordinary cycle. Ancient stars die in violent explosions, scattering heavy elements through space and creating shock waves that compress interstellar gas. This compressed gas, now enriched with elements created by the dead star, collapses to form new stars. These new stars, in turn, can form rocky planets using the heavy elements left by their predecessors. And here's one of the most fascinating discoveries of modern astronomy. This cycle is accelerating. The first stars in the universe were composed almost entirely of hydrogen and helium. They lived, died, and enriched interstellar space with heavier elements. The second generation of stars already had a small amount of heavy elements, which allowed the formation of the first rocky planets. The third generation had even more heavy elements, enabling more complex planets, and, eventually, the conditions necessary for life. Our Sun is a third-generation star, born from material previously enriched by at least 2 previous generations of supernova explosions. That's why the solar system could form rocky planets like Earth, with iron cores, water oceans, and atmospheres rich in elements necessary for life. Have you ever wondered how many stars had to die for you to exist? How many cosmic violent explosions were necessary to create the conditions that allowed Earth's formation, life's evolution, and eventually the emergence of consciousness? It's a chain of events so improbable and yet so inevitable that it borders on the miraculous. Not everything is completely destroyed in a supernova explosion. At the center of the destruction, something extraordinary remains, a remnant that defies our intuitions about matter and space. Depending on the original star's mass, this remnant can be one of the 2 most extreme things we know in the universe, a neutron star or a black hole. If the original star had between 8 and 25 solar masses, what remains after the explosion is a neutron star, an object so dense and bizarre it seems straight out of a science fiction novel. Imagine compressing all the mass of our Sun into a sphere only 20 kilometers in diameter. The resulting density is so extreme that a teaspoon of this material would weigh 6 billion tons, approximately the same weight as an entire mountain. To understand how dense a neutron star is, consider this analogy. If we could compress all of humanity, all 8 billion people on Earth, with the same density, we would all fit in the volume of a sugar cube. It's a density that completely redefines our understanding of matter, where the very laws of physics we know on Earth are taken to their absolute extreme. But neutron stars aren't just dense. They also possess magnetic fields, billions of times more intense than anything we can create on Earth. These magnetic fields are so powerful they would distort atoms into elongated shapes if you got close. And they spin not slowly like planets, but hundreds of times per second, some completing a full rotation in milliseconds. Imagine an object with the Sun's mass spinning faster than helicopter blades. Centrifugal force should tear apart any normal material, scattering it through space like water drops from a centrifuge. But a neutron star's gravity is so intense, minus 200 billion times stronger than Earth's gravity, that it holds everything together against these extreme forces. Some neutron stars manifest as pulsars, cosmic lighthouses that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep through space like lighthouse lights. And if we're aligned with the beam, we detect regular pulses of radiation. Some pulsars are so precise they rival Earth's best atomic clocks. Have you ever wondered what it would be like to be near one of these objects? Obviously, it would be fatal. The intense gravity would create tidal forces that would stretch your body like spaghetti long before you got close. Astronomers call this, with a touch of dark humor, spaghettification. But even at a safe distance, the environment would be alien beyond imagination. If the original star was even more massive, more than 25 solar masses, then not even the degenerate pressure of neutrons can resist gravitational collapse. The core continues collapsing until it forms a black hole, a region of spacetime where gravity becomes so intense that not even light can escape. Black holes are perhaps the most mysterious objects in the universe. They represent points where our understanding of physics reaches its limits. At the center of a black hole, all known laws of physics break down. Density becomes infinite, time stops, and the very concept of space loses meaning. But even being invisible by definition, black holes leave their mark on the universe. They distort spacetime around them, bending light from distant stars and creating gravitational lensing effects. If material falls into a black hole, it forms an accretion disk that shines intensely due to frictional heating, becoming one of the most luminous objects in the universe. In 2015, science reached a historic milestone when we detected gravitational waves, ripples in the very fabric of space-time, produced by the collision of two black holes more than 1 billion light-years away. It was as if we had developed a new cosmic sense, capable of hearing the most violent events in the universe. And in 2019, we managed for the first time to photograph a black hole, or more precisely, the shadow it casts on the bright material around it. The black hole at the center of galaxy M87, with a mass 6.5 billion times greater than the Sun, was revealed as a perfectly circular dark region surrounded by a ring of orange light. These supernova remnants aren't just cosmic curiosities. They continue influencing the universe around them for billions of years after the original explosion. Neutron stars can accelerate particles to near light speeds, creating cosmic rays that constantly bombard Earth. Black holes can regulate star formation in entire galaxies, controlling the flow of gas and energy through vast regions of space. Each of these extreme objects is a natural laboratory, where we can study physics under conditions impossible to recreate on Earth. They allow us to test our most fundamental theories about the nature of matter, energy, space, and time, in the most extreme environments the universe can offer. Throughout human history, our ancestors were occasionally gifted with the spectacle of a supernova exploding in our galaxy. These events were interpreted differently by various cultures, but all left their marks on human history and mythology, serving as reminders that the universe is a dynamic place in constant change. One of the most famous supernovas in history was observed by Chinese astronomers. On July 4, 1054 AD, they described it as a guest star that suddenly appeared in the constellation Taurus and shone so intensely it was visible during the day for 23 consecutive days. During the night, it remained visible to the naked eye for almost 2 years, a spectacle that must have caused wonder and possibly fear in people of that era. Chinese records are poetic in their description. Visible during the day like Venus, with pointed rays in all directions, reddish-white in color. They noted that the star was so bright it could be seen even when the sun was in the sky, an extraordinary astronomical feat only possible with the most luminous cosmic events. Can you imagine the impact this event had on people of that time? Suddenly, a new star appeared in the sky, brighter than any other, challenging the widely accepted belief that the heavens were immutable and eternal. For a civilization that observed the night sky with the regularity we check the weather, the sudden appearance of a new star must have been as surprising as if a new sun appeared in the sky today. What remained from that 1054 explosion is one of the most studied and photographed nebulae in modern astronomy, the Crab Nebula. When we observe this nebula through modern telescopes, we see a filamentary and colorful structure, expanding through space at thousands of kilometers per second, still echoing the explosion our ancestors witnessed almost 1,000 years ago. At the center of the Crab Nebula lies a pulsar, a neutron star spinning 30 times per second, emitting regular pulses of radiation like a cosmic lighthouse. It's the compressed core of the star that exploded in 1054, now transformed into one of the densest objects in the universe, serving as a natural laboratory for studying physics under extreme conditions. On November 11, 1572, the famous Danish astronomer Tycho Brahe was walking from his alchemy laboratory to home when he noticed a new bright star in the constellation Cassiopeia. He described it as brighter than Venus and initially thought he was seeing something in our atmosphere, perhaps a very bright comet. But when Brahe realized that the new star showed no parallax, that is, it didn't change relative position as Earth moved in its orbit, he understood he was observing something in the depths of the cosmos, far beyond Earth's atmosphere. This observation was revolutionary because it directly challenged the dominant Aristotelian ideas that the heavens were perfect and immutable. Tycho's supernova, as it became known, remained visible for more than a year, gradually changing color from bright white to yellow, then orange, and finally red before disappearing from sight. Brahe documented these changes meticulously, creating one of the first detailed scientific studies of a supernova. This event was one of the observations that helped establish a new era in astronomy, showing that the universe was a dynamic place in constant change. It was a blow against ancient cosmology that saw the heavens as a perfect and immutable crystalline sphere, and helped pave the way for the scientific revolution that would follow. In 1604, just 32 years later, another supernova appeared, this time in the constellation Ophiuchus. Observed by Johannes Kepler and other astronomers of the time, this would be the last supernova visible to the naked eye in our galaxy to this day. Kepler's supernova shone for more than a year and was studied by observers around the world, marking the end of an era of visible supernovas in our galactic neighborhood. Have you ever thought about what it must have been like for these early observers? Without knowledge of stellar physics, without understanding of cosmic scale, suddenly witnessing the birth of a new light in the sky. For them, it must have seemed as if the very fabric of reality was being rewritten before their eyes. These historical observations weren't just milestones in astronomy. They fundamentally changed our understanding of our place in the universe. They showed that the heavens weren't immutable, that stars could be born and die, and that the cosmos was a much more dynamic and interesting place than previously thought. Today, we know that supernovas explode in our galaxy approximately once every 50 years, but most are obscured by interstellar dust and aren't visible to the naked eye from Earth. Modern astronomers use space telescopes and sensitive detectors to study these explosions in our galaxy and in distant galaxies, revealing the physical secrets our ancestors could only imagine. With the advent of modern telescopes and space astronomy, our ability to study supernovas has been completely revolutionized. Today, we detect hundreds of supernovas per year in distant galaxies, each offering precious clues about the evolution of the universe and the physics of the most extreme events in nature. One of the most surprising and revolutionary discoveries of recent decades came from studying type Ia supernovas in very distant galaxies. In the 1990s, two independent teams of astronomers were using these supernovas as standard candles to map the expansion of the universe. Since all type Ia supernovas explode when the white dwarf reaches exactly the same critical mass, they have approximately the same intrinsic brightness, making them ideal tools for measuring cosmic distances. But when these teams analyzed the data, they discovered something completely unexpected. The distant supernovas were fainter than they should be, indicating they were farther away than expected based on the universe's age and known expansion rate. There was only one possible explanation. The universe isn't just expanding, but its expansion is accelerating. This discovery was so surprising that astronomers initially doubted their own data. After all, gravity should be decelerating the universe's expansion, not accelerating it. But subsequent observations confirmed the result, leading to the discovery of dark energy, a mysterious force that permeates all of space and is accelerating the universe's expansion. Can you perceive the profound irony in this? By studying the death of stars, we discovered something fundamental about the birth and destiny of the universe itself. The violent explosions of distant stars revealed to us that our cosmos is dominated by a form of energy we don't fully understand, but which represents about 70% of everything that exists. This discovery earned the 2011 Nobel Prize in Physics for the leaders of both research teams and fundamentally changed our understanding of cosmology. It showed that the universe wasn't just born in an explosion, the Big Bang, but is destined for eternal accelerated expansion, eventually resulting in a cold and diluted cosmos where stars go out one by one. Type Ia supernovas are so useful for measuring cosmic distances that astronomers call them cosmic standard candles. It's as if the universe had given us lanterns of known power scattered throughout the cosmos, allowing us to map distances to the most remote galaxies. And all these lanterns are actually dead stars exploding with unimaginable violence. On February 23, 1987, astronomers were gifted with an extraordinary event. A supernova exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way just 160,000 light-years away. It was the closest supernova observed since the invention of the telescope, offering a unique opportunity to study these events in unprecedented detail. Supernova 1987A, as it was named, was initially detected not by optical telescopes, but by neutrino detectors, ghostly particles that rarely interact with matter. About 3 hours before the explosion became visible, detectors in Japan and the United States recorded a burst of neutrinos coming from the direction of the Large Magellanic Cloud. This detection was extraordinary for several reasons. First, it was the first time neutrinos from a supernova were detected, dramatically confirming our theories about stellar core collapse. Second, the fact that neutrinos arrived hours before visible light confirmed they're produced during the initial core collapse, while the visible explosion results from the shock wave that takes time to traverse the star's outer layers. The neutrinos from SN 1987A traveled 160,000 light-years through space, passed through all of Earth, including the detectors, and continued traveling through space on the other side. For them, our entire planet was just a small transparent obstacle in their cosmic journey. The fact that we managed to detect some of them was a triumph of engineering and experimental physics. Supernova 1987I also brought surprises. The star that exploded, a blue supergiant called Sangelek-69202A, wasn't the type of star we expected to become a supernova. Our models predicted that only red supergiants should explode, but here was a blue supergiant doing exactly that. This discovery forced astronomers to revise their theories about stellar evolution and showed that the universe still had surprises to teach us. It also demonstrated that supernovas are unique natural laboratories for testing our understanding of physics under extreme conditions we can never replicate on Earth. Today, automated telescopes continuously scan the night sky, searching for new supernovas. Projects like the Palomar Transient Factory and the All-Sky Automated Survey for Supernova ASASN discover dozens of supernovas per month, creating an unprecedented database of these cosmic events. Each new discovery adds another piece to the puzzle of our understanding of supernovas and the universe. Some confirm our existing theories, while others, like the discovery of superluminous supernovas that shine 100 times more intensely than normal, challenge our understanding and force us to expand our physical models. At the extreme frontiers of our understanding about stellar explosions, we encounter events even more violent that challenge even our imagination expanded by common supernovas. Some stars aren't content to explode as typical supernovas. They produce hypernovas, explosions so violent they release 10 to 100 times more energy than a common supernova. To put this in perspective, remember that a normal supernova already releases more energy in a few seconds than the Sun will produce during its entire 10 billion year life. Now imagine an event 100 times more energetic. It's an amount of energy so vast it defies our capacity for understanding, like trying to imagine a number with 100 zeros. These hypernovas are intimately associated with the most energetic events we know in the universe, gamma-ray bursts or GRBs. Imagine a cosmic lighthouse that, for a few seconds or minutes, emits more energy than hundreds of billions of galaxies combined. It's so much concentrated energy that, if a gamma-ray burst occurred a few hundred light-years from Earth and were directed at us, it could instantly extinguish life on our planet. The discovery of gamma-ray bursts was, ironically, a byproduct of the Cold War. In the 1960s, the United States launched a series of military satellites called Vela to detect secret Soviet nuclear tests in space. These satellites were equipped with sensitive gamma-ray detectors, designed to capture the characteristic signature of nuclear explosions. Instead, the Vela satellites began detecting mysterious bursts of gamma rays coming from random directions in space. These bursts were completely different from anything known. They appeared without warning, shone intensely for a few seconds or minutes, and then disappeared completely, never repeating in the same location. For decades, gamma-ray bursts remained one of astronomy's greatest mysteries. Were they local events in our galaxy or distant and extremely energetic phenomena? The controversy was only resolved in the 1990s, when precise distance measurements revealed these bursts were occurring in galaxies billions of light-years away. The mechanism behind these extreme events is still the subject of intense research, but the most accepted theory connects them to the formation of very massive black holes that spin rapidly. When an extremely massive star, perhaps with more than 40 solar masses, collapses, it can form a black hole that spins so rapidly it distorts spacetime around it in extraordinary ways. This extreme rotation can create jets of matter and energy that shoot from the black hole's poles at speeds close to light speed. When these jets traverse the outer layers of the exploding star, they create the gamma-ray bursts we can detect at cosmological distances. It's as if the newly formed black hole were a cosmic cannon firing pure energy through the universe. Have you ever wondered why the universe allows such extreme events? Why nature created processes capable of releasing energy equivalent to the simultaneous explosion of trillions of hydrogen bombs? Perhaps because on cosmic scales, even the most unimaginable violence serves a fundamental purpose. These extreme explosions may have been responsible for creating and dispersing some of the heaviest and rarest elements in the universe. During a hypernova, conditions are so extreme that nuclear processes impossible anywhere else can occur. Elements like gold, platinum, and uranium, essential for modern technology and possibly for advanced life forms, may be produced in abundance only during these most violent events. Furthermore, gamma-ray bursts may have played a crucial role in the evolution of life in the universe. Some scientists theorize these explosions may have caused mass extinctions on nearby planets, but they may also have provided the energy necessary to drive complex chemical reactions in primitive planetary atmospheres. There's even a controversial theory that a relatively nearby gamma-ray burst may have caused one of Earth's mass extinctions, specifically the Ordovician-Silurian extinction about 450 million years ago, which eliminated about 85% of all marine species. If this theory is correct, then life's evolution on Earth was influenced by the violent death of a star in a distant galaxy. Studying these extreme events also helps us understand the physical limits of the universe. Gamma-ray bursts allow us to test our understanding of general relativity under conditions we can never recreate in a laboratory. They show us how matter behaves when accelerated to 99.99% of light speed, how spacetime responds to extreme gravitational fields, and how energy can be converted to matter on cosmic scales. Each gamma-ray burst we detect is like a fundamental physics experiment happening billions of light years away. They're natural laboratories where the laws of physics are tested at their absolute limits, offering insights we couldn't obtain any other way. Looking to the future, our understanding of supernovas continues evolving with increasingly sophisticated technologies. New telescopes, both on Earth and in space, are detecting supernovas in unprecedented numbers, allowing statistical studies that reveal previously invisible patterns in the cosmic symphony of stellar death. One of the most exciting frontiers is the detection of gravitational waves, ripples in the very fabric of spacetime, produced during the most violent events in the universe. In September 2015, LIGO detectors first recorded gravitational waves produced by the collision of two black holes more than 1 billion light-years away. It was as if we had developed a new cosmic sense, capable of hearing the music of the spheres in a completely literal way. In 2017, we witnessed something even more extraordinary: the simultaneous detection of gravitational waves and visible light from a cosmic event. Two neutron stars, each with our sun's mass compressed into a city-sized sphere, orbited each other in increasingly rapid spirals until they finally collided in an explosion that created heavy elements like gold and platinum. This detection opened a new era in astronomy, the era of multi-messenger astronomy, where we can study cosmic events using gravitational waves, visible light, X-rays, gamma rays, and even neutrinos simultaneously. It's as if we had developed multiple senses to observe the universe, each revealing different aspects of the same dramatic phenomena. Astronomers are also developing increasingly sophisticated methods to predict which stars will explode as supernovas and when this might happen. Through detailed study of massive stars in our galaxy, we can identify candidates that are in the final stages of their lives and might explode within a few thousand or million years, a blink of an eye in cosmic terms. One of these candidates is Betelgeuse, the famous red star that marks Orion's shoulder. This red supergiant, with approximately 20 times the Sun's mass and 700 times its diameter, has shown intriguing signs of instability in recent years. In 2019 and 2020, Betelgeuse significantly dimmed, leading some to speculate whether it might be approaching the end of its life. If Betelgeuse exploded as a supernova, and this could happen tomorrow, In 1,000 years or in 100,000 years, it would be an unprecedented spectacle in modern human history. The explosion would be visible during the day for weeks, appearing like a second moon in the night sky. It would be the brightest supernova observed by humanity since we developed modern telescopes and detectors. Can you imagine the scientific and cultural impact this would have? A familiar star, part of one of the most recognizable constellations in the sky, suddenly transforming into a cosmic beacon that would change the night sky's appearance for future generations. It would be a dramatic reminder that we live in a dynamic universe where even stars we consider eternal are subject to dramatic changes. But Betelgeuse isn't the only supernova candidate in our cosmic neighborhood. Stars like Eta Carinae, one of the most massive stars known in our galaxy, are also in the final stages of their lives. Eta Carinae is so unstable it has already experienced smaller explosions in the past, including an eruption in 1843 that temporarily made it the second brightest star in the sky. The development of next-generation space telescopes, like the James Webb Space Telescope, is revolutionizing our ability to study supernovas in distant galaxies. This telescope can detect infrared light from supernovas that exploded when the universe was young, allowing us to study how these events evolved throughout cosmic history. One of modern astronomy's most fascinating discoveries is that the universe's first stars, called population 3 stars, were very different from stars we see today. They were composed almost entirely of hydrogen and helium, without heavy elements, and were probably much more massive than any modern star. When these primitive stars exploded as supernovas, they were responsible for creating the universe's first heavy elements. The James Webb and other next-generation telescopes may be able to detect these primordial supernovas, observing events that occurred just a few hundred million years after the Big Bang. It would be like watching the first chapters of the universe's chemical history, when the elements that make complexity and life possible were created for the first time. Another exciting development is the use of artificial intelligence and machine learning to analyze supernova data. With hundreds of supernovas being discovered each year, it's humanly impossible to analyze each one in detail. Sophisticated algorithms can now automatically classify different types of supernovas, identify unusual events that merit additional study, and even predict some supernova properties based on initial observations. These technological advances are allowing us to study supernovas with a level of detail that would have been unthinkable just a few decades ago. We can now map how elements are distributed during an explosion, study shockwave physics in real time, and even detect the first hours after an explosion begins. But perhaps the most exciting development is our growing ability to connect supernovas to other cosmic phenomena. We're discovering that these explosions aren't isolated events, but part of a complex network of processes that shape entire galaxies' evolution. They regulate star formation, distribute heavy elements, heat intergalactic gas, and may even influence supermassive black hole formation in galaxy centers. The future of supernova research promises to reveal even more surprising connections between these violent events and the fundamental processes governing the universe. Each new discovery brings us closer to a complete understanding of how supernovas shaped the cosmos we live in and continue to influence its future. We now come to the end of our journey through the explosive cosmos of supernovas, but also to the beginning of a deeper understanding of our own existence. All the stories we've shared about collapsing cores, elements being forged at unimaginable temperatures, shock waves sweeping through interstellar space, converge into an extraordinary, poetic truth that connects your existence to events that occurred billions of years before you were born. You are a direct consequence of these violent cosmic events. Every breath you take contains oxygen forged inside a massive star billions of years ago. The calcium in your bones was created during nuclear fusion of lighter elements in the burning heart of a supergiant. The iron that transports oxygen in your blood was born in the final moments of a giant star's life, when radiation pressure finally succumbed to relentless gravity. But the story doesn't stop there. When you eventually return to Earth, when the atoms forming your body disperse, they will continue their cosmic journey that began billions of years ago. Some may be incorporated into plants, others may evaporate into the atmosphere, and some may even, on geological timescales, find their way back to interstellar space. There, floating in the apparent void between stars, these atoms will patiently await their next cosmic adventure. Perhaps billions of years in the future, a new supernova shockwave will push them into a collapsing molecular cloud. Perhaps they'll become part of a new star, a new planet, or even a new form of life on a world that doesn't yet exist. The supernova cycle is in reality the cycle of existence itself. Death and birth, destruction and creation. Ending and beginning, all intertwined in a cosmic dance that connects the smallest particles to the largest structures in the universe. Supernovas aren't just distant astronomical events. They're the fundamental processes that made complexity, life, and eventually consciousness possible. Think about the extraordinary chain of events that had to occur for you to exist at this moment. Generations of stars had to be born, live, and die violently over billions of years. Elements had to be forged in nuclear furnaces of unimaginable temperatures. Shock waves had to compress interstellar gas clouds until new stars and planets could form. And all this had to happen in a perfect sequence over 13.8 billion years of cosmic history. Have you ever wondered about the profound philosophical implications of this? If we removed any of the supernovas from cosmic history, if we slightly altered the mass of any of the stars that exploded, if we changed the timing of any of these explosions, you wouldn't be here now. Your existence depends on a cosmic symphony of stellar deaths that began long before Earth even existed. This leads us to a perspective of profound humility about our place in the universe. We aren't external observers of this great cosmic dance, we're active participants, made of the same substance as stars, carrying in our bodies the history of explosions that illuminated entire galaxies. We are the universe that developed consciousness, fragments of ancient supernovas that learned to contemplate their own origin. At the same time, this understanding connects us intimately with the cosmos. When you look at stars in the night sky, you're not observing distant and alien objects. You're looking at your cosmic ancestors, at the nuclear furnaces that created the elements in your body, at the beacons that illuminated the universe during its turbulent youth. And here's perhaps the most profound reflection of all. Supernovas teach us that destruction and creation aren't opposing forces, but different aspects of the same fundamental process. A star's violent death isn't an end, but a transformation. It's the universe's way of ensuring that complexity continues growing, that new worlds can be born, that life can flourish in still unexplored corners of the cosmos. Each supernova is simultaneously a lament for worlds that may have been destroyed and a song of hope for worlds yet to be born. It's the universe constantly reinventing itself, ensuring that cosmic history never ends, only changes chapters. It's proof that even in moments of greatest violence and destruction, the seeds of creation and beauty are being planted. When we contemplate supernovas, we contemplate our own transitory nature and, paradoxically, our eternal connection to something much greater than ourselves. We are temporary arrangements of stardust that develop the extraordinary capacity to understand their own cosmic origins. We are fragments of ancient explosions that learn to marvel at the violence that created them. Carl Sagan captured this poetic truth when he said, "We are made of star stuff." But this statement goes beyond mere poetry. It represents one of humanity's most profound scientific discoveries. It reveals that there's no real separation between us and the cosmos. We are the universe looking at itself, dead stars contemplating their own legacy. Supernovas also teach us about the inevitability of change and transformation. Just as stars cannot avoid their eventual death, we too are part of larger cycles of transformation. But instead of seeing this as frightening, supernovas show us that transformation can be an act of supreme creation. A star's death enables the birth of entire worlds. And now, as our journey through supernovas comes to an end, I want to deeply thank you for accompanying me on this extraordinary exploration. Thank you for sharing these hours contemplating the mysteries of the cosmos, for allowing your mind to travel through scales of time and space almost incomprehensible. Thank you for having the courage to confront the vastness of the universe and finding in it not terror, but wonder and connection. I hope that the next time you look at the night sky, you remember this story. I hope you see not just distant points of light, but an interconnected network of stellar births and deaths that culminated in some miraculous way in your conscious existence. I hope you feel the profound connection you have with every star that shines, knowing you're made of the same substance they are. Supernovas teach us that we're all made of the same fundamental substance, that we share a cosmic heritage connecting us not just to each other, but to everything that exists in the universe. They show us that beauty can emerge from the most extreme violence, that creation can arise from total destruction, and that life can flourish in the most unlikely and extraordinary places. Most importantly, they reveal that our existence isn't an insignificant accident in an indifferent universe, but rather the inevitable result of billions of years of cosmic evolution. We are the universe that developed eyes to see itself, minds to understand itself, and hearts to admire itself. We are the way the cosmos found to contemplate its own magnificence and complexity. What if everything we are, everything we love, all our dreams and hopes, all our tears and joys, were really direct consequences of the violent explosion of stars that died billions of years before we were born? What if our capacity to love, to create art, to do science, to contemplate our own existence, to feel compassion for one another, were simply the universe developing an extraordinary way to understand itself through conscious fragments of ancient supernovas that learned to dream?